Hello, this is Orlando Castilleja. Today we're going to perform a simulation using SOLIDWORKS Flow Simulation. And this simulation is about the flow of air within a classroom. We have in this case two components. The first one is air and the second one is CO2. And in this case we want to demonstrate how to use some design features. For example, convert entities, extruded hot and extruded both days. And we want to simulate the transfer of multiple species. We also want to demonstrate how to specify the presence and the concentration values of multiple species, and we want finally to demonstrate how to specify a time-dependent model. What we are asked to determine here is we want to obtain the velocity and the volume flow rates of air at each outlet at 16 seconds after the start of the process, and we want to calculate the average concentration of CO2 at each outlet after the same period of time. Later we want to show the flow trajectories for the CO2 mass fraction at different times, and finally we want to show at least 6 contour plots or cut plots for the velocity, the pressure within the domain. Okay, the geometric features are given here in this slide, and the boundary conditions are these ones. We are going to specify that we have an inlet boundary condition in the door of the domain of the classroom, and we have an initial concentration within the classroom of 900 parts per million, and we are going to be replacing that air with fresh air with a concentration of 400 ppm. Okay, the outlets will be specified as a hole in the roof and the 3 windows. All the other boundaries are the walls. At the end we will end up with some plots like this one. This is showing the flow trajectories at different times, and you can see how the concentration, the mass fraction of carbon dioxide is changing in time. Here I have times up to 60 seconds, but you can obtain values beyond that point. These are the contour plots or the cut plots for the velocity and pressure distribution, and you can also obtain some specific values or parameters, obtaining the surface parameters for the velocity, the volume flow rate, and the concentration of CO2. In this case we have an animation, and it's showing a cloud type of cloud, like where you can see how the concentration of CO2 is changing in time. Here you have something similar but in another view. And in the plot you can see how the concentration of how the mass fraction of CO2 is changing in time also. Okay, this is the same plot, and these are the conversions for the parts per million to fraction, mass fraction. Okay, we're moving on to the software, and I'm going to create a new document, a new part. Okay, I'm going to start from the top plane, and I'm going to start a new sketch. Click top plane and click sketch. There I'm going to select from the sketch menu a corner rectangle, and I'm going to start drawing from this reference point, the origin point. Okay, I'm going to use the smart dimension function, and I'm going to specify here that the length of this rectangle is 5 meters. I'm going to type 5m, and for the side will be 4 meters. There you go. Now I'm going to the features menu and I'm going to extrude this surface, and the extrusion will be 3 meters. But if I extrude it this way, I will end up with a solid, but I don't want a solid, I want a hollow geometry. So I will activate here the thin feature, and I will specify a thickness of 150 millimeters. And as you can see, we have something like this. So this will be our walls. It really doesn't matter how much you specify here, because the software will won't take into consideration this thickness, but we just want to specify that the fluid is contained within this domain. Okay, let's keep it like this. So we're going to click OK. Now we want to define the roof and the floor. So I'm going to zoom in here, and I'm going to position on this surface. I want to select this surface, not the edge, but the surface. And I will click here in sketch, in this little box that pop up, and sketch. Okay, now I'm going to select all the edges. In this case is the edges, the outer edges, and I will use the control key to select the 4 edges of the rectangle. And in the sketch menu I will select convert entities, and as you can see in the sketch or the plane in which we are working on, now we have a rectangle that was copied from the edges we had before. So we will use this rectangle to extrude it using extruded boss base, and we will define a thickness of 150 millimeters. Okay, it is not the thickness, it's actually the extrusion dimension or length. Okay, now we're going to do the same on the other side. So to change the plane in which we are working on, I'm going to zoom in here. I'm going to click on the surface, and I will click sketch. Now we're working on a new sketch, and we're going to copy the entities, or we're going to convert these entities. So you have to select the 4 edges with the control key at the same time, and convert entities. Here, convert entities. So there you have the rectangle, and I'm going to features, extruded boss base, and you can see that we have the same thickness of the other operation, from the other operation. Okay, there you go. I'm going to use the isometric view. There you have. So now I want to generate the door, the windows, and the fan or a structure on the top, on the roof. So I'm going to click here in the surface to start drawing there, and I will click sketch, and I will use the corner rectangle. I will position here, and make sure that you have this reference line, the construction line, and we can draw something like this, and later we can specify the dimensions of the door. It is 1200 here, and in height is 2 meters. Okay, I'm going to move this. Okay, and I'm going to specify here that we have a thickness or a distance of 150. This is because we have to respect the dimension of the floor, remember. Okay, now we have to specify also the distance from the left edge to the left edge of the door. So in this case is 500 millimeter, and there we have. So we're going to make a extruded cut here. I'm going to features, extruded cut, and we have a pre-visualization of the operation, and I'm going to click OK, and we can verify if this is okay, and I think it's okay. So now we're going to draw the windows, position on this surface, click on this surface, and then click on sketch, and start drawing a rectangle. And you can specify the dimensions according to our blueprints is 1 meter here, and in this case 1.5 meter. And we know that the distance from the bottom is also 1 meter, and the distance from this side we can specify 650. And now we have to use a linear sketch pattern from the sketch menu. We're going to replicate this pattern. In this case I'm going to specify 3 elements, and I think here we can specify well, okay, 1500, and you will end up with something like that. So I'm going to features, extruded cut, and I will make sure that we have the dimensions that we need. I think it's okay, and okay, and there's the window. There you have the windows. Now finally we have to generate the extruded cut, but for the fan or the extractor on top. So click on the roof, sketch. I think I have to generate it here, so I will use from the sketch menu a circle and smart dimension. I think that here is 900, and here 1 meter. There you go. Go to features, extruded cut, and okay. There you have. Remember that you have to save this work. Okay, and we're going to flow simulation. Remember, if you don't have this tab, you can go to SOLIDWORKS add-ins, and you can click here to activate the SOLIDWORKS Flow Simulation. If you can also find it here in add-ins and look for SOLIDWORKS Flow Simulation, that is here, and activate both checkboxes. So click OK, and I'm going to flow simulation, tools. Remember that when you have an internal type of analysis, you have to create the leads. So click tools, create leads, and we're going to click the adjacent surfaces that have holes. So you can select these three surfaces and click OK. So I'm going to save the work, and we're going to wizard. Here you can specify a name for the project. Okay, click next. And it's an internal type of analysis because we have a defined geometry, and within this geometry the fluid is flowing. So we need to specify time dependent because it's a time dependent model, and we will simulate 60 seconds and a time step of 5 seconds. The gravity will be acting on the y direction, and the component is C. Rotation no, and free surface no. Okay, next. We have to specify two gases. In this case is air and carbon dioxide. The flow characteristics or flow type is laminar and turbulent in this case, and next. And we can specify the concentrations. Remember that the initial concentration of carbon dioxide in air is 0.0009, and to complete the unit we have to specify 9991. Okay, finish. Okay, now we know that the computational domain is within the geometry because we don't need to model or to simulate the part of the walls, the solid part. We will define the boundary conditions. First we need an inlet boundary condition that will be specified here in the door. Remember something, if you click directly here in this surface or in this boundary, you will end up with a warning here that this face that you just selected is out of the computational domain. To avoid this message, you have to come back here, inlet mass flow 1, clear this selection, and you have to come here, right click on the surface that you need and select other, and you will select from these options the first one, face at lead 2, or you can also select this one, the lead to a classroom. So I will select the first one, and now I will be able to click OK without problem. This is because the surface, for example this one or this one or this one, is out of the computational domain. The computational domain, I showed you that it was in this mark geometry within the solid, is not coincident with this survey, with this surface. This surface is outside of the computational domain, so the software won't recognize this surface. So you have to do what I told you. Okay. I will specify here inlet velocity, and the velocity will be 1 meter per second. I will specify also the substance concentration and its mass fraction. I'm going to change a value here because the fresh air has a lower concentration of CO2. We want to replace that higher concentration with a lower concentration air. Okay, you can click OK. And now we will add a new boundary condition, and this boundary condition will be a pressure opening type of boundary condition, and will be environment pressure. This is for the outlets that are this one, this, and this. What you're specifying there is that the pressure in that boundaries is the environment pressure, one atmosphere, that is specified here. We also have the temperature, but in this case we don't worry much about the temperature. Okay. So we don't need to specify the what, because by default the solver is assuming that you have the no-slip boundary condition on all the solid surfaces. And we can specify goals here. I'm going to add a new goal. I'm going to insert global goals, and we want to calculate with this global goal is the mass fraction of carbon dioxide. And what the solver will do is to calculate what is the mass fraction. I think that it was the mass fraction. The mass fraction of carbon dioxide. We need the average value, so click OK. I'm going to delete this one. Okay, we deleted the other one, and we're going to continue with this one. This global goal is to calculate what is the average mass fraction of carbon dioxide within the complete domain. What will the solver do is calculate the mass fraction of all the air that is inside. Okay, then we will use this value to plot against time. The global mesh, we can visualize the global mesh here. We also can change the transparency of the model, display transparency, and set it to 90%. And if we want to refine the mesh, we can increase the value, the level here. I think that 6 is okay. And you can see here the indicators that you have some boundary conditions specified over there. I'm going to hide the mesh, and I think that we can already run the simulation, new calculation, and run. Okay, the solver is finished. And we can start creating or retrieving the information that we need. For example, let's start with the surface parameters. Here we are going to add a new surface parameter. And I'm going to select this surface, select color, lead 5. And we want to know what is the, for example, the mass flow rate of air, the mass fraction of CO2, the velocity here in this window, and the volume flow rate, and show. And you have all this information here. This is for time 60 seconds. In other words, it's for the final time that we specified. And you can see that the average mass fraction is 0.005. That is a little bit lower than the original concentration. We have a average velocity of 0.5, and remember that we specify an inlet velocity of 1 meter per second. Okay, the volume flow rate is this one, and the mass flow rate is this one. So you can do the same for all the other windows. I'm going to clone, and I'm going to change the boundary. Okay, here you have these values. Okay, here you can see the difference between the velocity values and mass fractions of CO2. If you want to know what is this value on other time step, on another time, I'm going to click here in results, right click, load time moment, and here you can change the time that you need. For example, you want to know what happens at 25 seconds, click OK, and now you have the update here. I'm going to hide this information, and you can also visualize here the cut plot. Okay, here we can move this plane up to here, and we want to visualize the mass fraction contours of carbon dioxide. We can increase this to 100 and obtain the preview. There we have. Okay, I'm going to click display by new, and we can create copies of this. I'm going to use clone. And I think I'm going to move it a little bit, for example 2 meters. I'm going to copy, clone, 3 meters. If you want, you can change the transparency here in options, 0.5. You can do the same for the other. And I'm going to add another one, but in this case I will add it on the top plane, and I'm going to move it 1 meter. I'm also going to specify 0.5 in transparency, and now we have something like this. If you want to change the time, for example, you want to go here, results, load time moment, and 5 seconds. Now you can see that we are starting here with the process of injecting fresh air. If you want to know what happens at the end of the process, or almost at the end, I'm going to 60 seconds, and you will end up with something like this. Okay. I'm going to make sure that we have the same reference, color reference for everything. So I'm going here, I'm going to click adjust minimum and maximum, and I'm going to specify here 4. Okay. I'm going to hide all. And we also can obtain the flow trajectories. Insert. And I'm going to start the trajectories from this surface. So select other. There you have. The number of elements will be 200. The elements will be arrows. And we will show the mass fraction of carbon dioxide. Click detailed preview. There we have. I'm going to set this value here. Okay. And we want to change the time to see the difference. So you can see that we have the inlet, the outlet, and the Windows outlets. You can always come back here to load time moment and change to any other time step. Okay, I'm going to hide this. Okay, now I'm going to move to the Transient Explorer, but before going to the Transient Explorer to see the videos or animations, I'm going to go to input data, calculation control options, and here I can see that the physical time that we are simulating is 60 seconds. We can increase or decrease this value, and in saving I have to activate here periodic because we want to use the Transient Explorer, and here we're going to start from 0 and the period will be 60, and we want to activate some parameters that we want to work with in the Transient Explorer. If we don't activate it before, we won't be able to use them. So I will double click here and I will select the mass fraction of carbon dioxide. It's something that I want to obtain, and I think that's all. Okay, and we have to run the simulation again. Maybe you will have these warnings, but don't worry about it. This is because sometimes the boundaries are large or so big, too big, and the vortices can be forming here, but you can ignore at this moment these warnings. So the solver is finished. And now we can go to results and click Transient Explorer. And for example, if we activate this, show all, we will be able to animate these plots. And now you can see an animation of how the mass fraction of carbon dioxide is changing in time. Okay, I can clone Of course, you can change also this parameter, for example, the velocity. But what we want to know is mass fraction of carbon dioxide. Okay, we're going to do something else, and we'll be using the goal plot, because remember that we specify a goal. So let's go to goal plots, right click on it, insert, and we're going to show how the average mass fraction of carbon dioxide is changing in physical time. Show. Okay, and I will right click here and show, and now we have this plot. Okay, and when we click here play, we will have an animation of what is happening inside this. It's an average value of all of the points within this domain, and is giving the average mass fraction of carbon dioxide. If you want to export this table to Excel, click export to Excel. You can save the file, and you can copy this plot, but you also can have the raw data here and create your own figures, your own plots. You can copy this table. Okay. Okay, let's review if we need something else about the project. The velocity and volume flow rate at, okay, this we have it. This also, flow trajectories, contour plots. Okay, that's all, the velocity and pressure. Okay, pressure. Pressure is not changing. Velocity is changing a little bit, but we want to know the mass fraction of carbon dioxide. How the air original in the classroom is being replaced by fresh air. Remember that fresh air has a concentration around 400 ppm of carbon dioxide. So this is the end of our tutorial. I expect that it's useful for you and that you can apply it in any of your future projects. I expect that you are doing well, and see you in the next tutorial. Goodbye.